So the universe is 13.7 billion years old. This is based on our recent measurement of the so-called Hubble constant using gravitational lensing. What we find is that the precision of our measurements of the properties of the universe are as good as the results of other cosmological probes. So there are various methods to measure the Hubble constant, the spatial curvature of the universe, and the dynamics of the dark energy. Gravitational lensing, which is what my collaborators and I use, is one method, and our study of the gravitational lens system, B1608 plus 656, is one of the most detailed and careful lensing analysis to date. So the neat thing is that the results of the several independent methods for measuring the properties of the universe are all agreeing with each other, which is giving us a consistent picture and understanding of the universe. Okay, let me explain the concept of gravitational lensing. Suppose this ball here is a massive object. If I shoot a light ray, without the ball, the light ray would travel in a straight line. In the presence of this massive object, the light ray would bend around the object due to the curvature of space-time according to relativity, general relativity from this object. So a light ray gets deflected, and the observer here sees the direction of light ray here, so it sees the ray originating from this position instead of from me. If the object is sufficiently massive, then it can create multiple images of the same source. So a light ray can first travel this path. So if I hold a candle and the first ray travels this path so that the observer sees the first image of the candle here. And another light ray of the candlelight can travel the second path and in this direction so that the observer sees the second image of the candlelight in addition to the first image. So this strong gravitational lens is creating multiple images of the same source, the same candlelight. B1608 plus 656 is one such multiple image system. So shown on the left is the Hubble Space Telescope image of the lens system. A background galaxy, a single galaxy, which we call the source galaxy, is lensed into 4 images, A, B, C, and D. The 2 galaxies G1 and G2 are acting as the gravitational lens and are therefore called the lens galaxies. The brightness of the core of the source galaxy is varying in time. This is shown in the top right panel of the radio observations of the source galaxy, where you see the changes in brightness. That is, each of the images are flickering. First, you'll notice that image B brightens up first, and followed by A, and then C, and finally D. The images brighten up at different times because the light ray from each of these images travel different paths. So back to our bending of light. The time it takes for this light ray to travel to the observer is different from the second light ray because of the path difference, that is, this path is shorter than this path, and also because of the gravitational time delay due to this massive object. The time it takes for a light ray to travel a short path can be longer than the time it takes to travel a longer path due to the gravitational time delay of the object. So an analogy of this gravitational time delay is the time delay due to in traffic conditions. So shown here is the Cologne time delays. Suppose we have 4 astronomers leaving Dusseldorf at the same time for the University of Bonn, and they take 4 different paths, as illustrated in these 4 different color lines: pink, green, blue, and red. Because the distance of each of these routes is different, and also the traffic condition on each of these routes is different, these 4 astronomers who leave Dusseldorf at the same time will arrive in Bonn at different times, just like how those 4 images, A, B, C, and D, are brightening up at different times. Suppose we're given this map here without the map scale, that is this little ruler that tells us how much 1 centimeter on this map corresponds to in kilometers in reality. We can actually figure out this map scale by observing and modeling this traffic system. So first, we measure the length of these paths in centimeter using a ruler. Second, we monitor when the astronomers arrive to compute the time delays. That is, the second astronomer is arriving 12 minutes later than the first, the third astronomer is arriving 19 minutes later compared to the first, and the fourth astronomer is arriving 28 minutes later than the first. The third thing we do is then we model the traffic conditions, that is, get the average speed on each of these routes. Because distance is speed multiplied by time, with the relative time delays from step 2 and the average speed from step 3, we can compute the difference in distance of each of these between these routes. Similarly, in a gravitational lens, we can compute the distance, the positions of each of those lens images, A, B, C, and D, from the lens galaxy. We can obtain the time delays by monitoring the brightness, just like we monitor when the astronomers arrive. And in the third step, we can model the gravitational lens system, just like how we model the traffic system. From these three things, we can then compute the Hubble constant, just like how we're computing the map scale. Our measurement of the Hubble constant is about 21 kilometers per second per million light years. In other words, a galaxy that is a million light years away is on average moving away from us at about 21 kilometers per second. A precise measurement of the Hubble constant is important because it tells us the age and the size of the universe.